Actually,
Okay. Yes.
I have a question.
Yeah, please.
So you have defined a reflection positivity for a quantum mechanics system, and you said that it's a collection of all these kind of symmetry, etc. There's never a precise definition for that.
No, I didn't give it a precise definition so you're right. So it was intentional. So I didn't wrote it down for Schwinger. So essentially, reflection positivity is a property of the Schwinger functions. Okay, I recall to you. So we defined the Schwinger functions, and they had three main properties. Somehow there should be some compatibility condition, which is the remnant of the algebraic structure of the initial algebraic structure of your problem. Then there is reflection positivity, and then there is an analytic condition, which also I didn't spell out properly. Okay, all this stuff takes a lot of time and all the detail to do it precisely. So I just wanted to hint to this thing. Maybe later on, even I can write it down, but it requires like 2000 index, and you don't. Okay, you write it down, and then you cannot do anything about it, essentially. Okay, so I wanted to give the feeling, what does it mean? And it's easier to express. It's easier to express for in our particular setting, and then essentially what happens more in general, that is, you can understand. So probably, if you assume that, okay, you can define, let me say like this, okay, you can define the notion of reflection positivity on probability measures, on stochastic process. Okay, so I can recall to you, I think we were more or less, yeah, I think I was discussing this, so recall from yesterday. So I didn't define in general, you're right, but actually I was precise when I define it for measure. Okay, so definition, the law of, so let me call the law P of a stochastic, or if you want, let me just be a stochastic process X. So we were in this context, okay. So you have a stochastic process. You need to have at least a time variable. You can have more variables. Of course, we can extend this in higher dimension, but at least there is one stochastic process is reflection positive. If and only if you have this condition, okay, for any. And then you want somehow the easiest condition, okay? Ideally, you want, okay, for any function, okay, for any bounded function f in C. So here I'm being, okay, let me, yeah, I wanted to say that it's measurable with respect to the future. So, okay, I can't say like this. Let me specialize to continuous, because I don't want to introduce a lot of detail. Let's say a continuous stochastic process for any bounded function f in whatever C. So this and continuous function from R plus could include 0 to R. Sorry. So this was. Okay, I was in my very easy setting of real valued continuous. Okay, let's say. In the complex number, one has, so this was the reflection positivity. So it's some, okay, I can even write it in this way, okay, in this context. This is positive, okay? Where, theta x, if you want theta x of t, okay, so is minus theta x, theta minus x, okay? This is another way to state the same thing, okay? Okay, so this is a precise definition, okay? And this will be like the definition which I will use when I will define. So for measure, I can be very precise because somehow the definition becomes simpler, okay? If you And then you can spell out what does it mean for Schwinger function. So from now on, somehow I think I don't need to discuss very much anymore Schwinger function, because as soon as you assume that the Schwinger function comes from the law of a stochastic process, then you can translate all your statement about statement in the stochastic process. Okay. Is this okay for you? So this will be my definition of reflection positivity, and that's precise, I think.
Yes, thank you.
Yeah. Okay. Yeah, of course. Then the point is why you make this strange definition, okay? And the reason you make this strange definition is because essentially from that you can rewrite what should mean on the Schwinger function, okay? It's essentially the same property, but I just wanted to give an idea how does it work, okay? I could look at the definition 2,000 times and don't get the idea if I don't see what is, because somehow the definition is a bit involved. Everything involving Schwinger function and Weidmann function is involved, because somehow there are a hierarchy of function depending on a variable number of parameters, which maybe, and I mean, I could write it down, but trust me, I don't get many insight from that. So I think this is fine. And this was the last point of, so yeah, thank you for the question. Anyway. Is this okay for you? Yes, maybe I didn't get. So this will be our definition, okay? You can imagine very well that your process can depend on other variables, but somehow reflection positivity refers to a particular symmetry. So it has to be an involution. You can think more abstractly, okay? You have an involution in the state space of your process. You need to have this somehow separation between, this involution should send somehow function in one subspace in the function in the other subspace, okay? So it's not an involution that does that, okay? So you need the freedom to, you have, okay, that's the, think about this situation. You have this time parameter, then you have function which are measurable only, which depend only on the positive times, and then you have this involution which send positive time to negative times, and vice versa. And then so this function actually it's measurable with respect to negative time. So okay, so there is this jointness of this operation. Okay, so the function should map space into, I mean, should separate separate the space of function into two subspaces essentially. Okay. Good. So this will be our definition. Then the last time we left you, so and we saw, okay, and we saw that among Gaussian process, only the combination, only linear combination of U or U processes satisfy this condition. And moreover, that symmetric Markov processes satisfy this condition. Necessarily, if and only. Okay, it's stringent. Okay, I didn't write again, but somehow. You have this condition for symmetric Markov processes. Okay, so Markov processes whose law is symmetric with respect to this transformation. Good, and it's an only if. Okay, if you have a Markov process and it's reflection positive, then actually it has to be symmetric. Okay. So I want to start from this because somehow, let's for symmetric Markov processes, you can describe quite precisely the reconstruction. Okay, so that's what I want to do now, because somehow it helps the intuition, I hope. So what was going on yesterday, for example? So how you so we did the road in one direction. So, and now I want to try to go back. Okay, just assuming that it's a symmetric Markov process. That's not what we are going to do in the end, because somehow it's difficult to prove that the measures we are going to construct, it's the law of a Markov process. Okay, so that's the difficulty. That's the difficulty in this business. That is, you lose very easily some properties. So you have to find what are the properties you can preserve in the approximations, or you can recover in the limit easily. Okay, so I will show you later. But keep in mind that there is this Markov way back. Actually, so you could ask, okay, why you make your fuss with this reflection positivity? Because we know that all symmetric Markov processes are reflection positive. So if I just prove that my process, that my measure, it's asymmetric, it's the law of a symmetric Markov process, I'm done. Okay, because then I can prove reflection positivity, and I trust what you said yesterday, and you can go back to the quantum problem. And the problem is really that it's not easy, and actually sometimes I think we don't even know if 543 is a Markov process. I mean, it's not easy. Maybe a posteriori you can prove something, but it's not easy to prove directly that the measure we are going to construct, the measure which interests us, it's a symmetric Markov process. And so reflection positivity is a weaker condition when the process is a Markov process is equivalent. So that's interesting. Yeah, but it's easier to prove. Sorry, I was not know what to say. So okay, so let's try to see. Anyway, let's try to see Markov process give a nice intuition. So let's try to see what's going on. I find interesting to show you. Today so we are going. Let's say, sorry, I don't see. To give a sketch of the reconstruction of the quantum mechanical data from a symmetric Markov process. Okay. So this give an hint, how does it work, this link between probabilistic data and quantum mechanical data. Okay? So I want to go back and construct the space and the space of observable and the dynamics, just knowing a symmetric Markov process. Okay, take the one you like more. Okay, I will show you later an explicit example. For example, it happens that this Gaussian, the Oster-Uhlenbeck process, which introduced the last time, is also a Markov process and is also a symmetric Markov process. So actually, we will use this example, a more explicit example. But let's do it just for knowing that it's a Markov process. Yeah, so the idea is that, so we consider the complex vector space. So where is the quantum mechanical Hilbert space? So in this case, you consider the complex vector space E plus. Yeah, of whatever cylindric. Yeah, let me, yeah, cylindric function supported on positive times. Okay, so this is the space entre functions. You could consider all the function, but it's enough just anyway. We will complete later on. Okay, so functions. These are functions which are made, for example, made out of trigonometric polynomials. Okay, you have coefficients, and then you have the process at positive times. Okay, there are many ways to write, okay, functions of the form like this for coefficients ck in complex number, lambda k in real numbers, tk in positive numbers. And okay, so you take this complex vector space, you call them cylindrical because just to evaluate very, very simple objects. And then you see this reflection positivity allow to endow, let's say endow this space. So let me, sorry, this space with a scalar product. Okay, and then you can imagine, okay, a Hermitian scalar product. Okay, you say how you take the scalar product to function. Well, you do what you expect. Okay, you introduce this theta, you take theta f times g. Okay, wait. Okay, recall that theta f was simply f composed with this inversion. Okay, in this notations. And you take here, of course, you take for any cylinder function. Okay, fg has to be cylinder. Okay, so this will be the scalar product, and I'm allowed to use it because of reflection positivity, and then we complete and we quotient, okay, or we quotient and complete, okay, whatever. So we let's see. Sorry, I'm lost in my notes. Okay, let me copy. So next step is that we take the quotient, n will be the subspace of element with zero norma, and then we complete, okay, to obtain an Hilbert space. And this quotienting, it's crucial here, okay? That's a very non-trivial operation. That's the point. There are many vectors. There are many functions which are in this quotient. So when you quotient, the space will become very, very much smaller than the space of all the functions defined on. Okay, imagine all these functions, and then of course when you take this scalar product, you get even more functions. Okay, actually here I could have started with all the measurable function on the positive semi-axis. That would not have changed much. Yeah. So what? So now this will be the Hilbert space. Okay. Now I have to introduce operators on the Hilbert space. And remember that we had, so our algebra of observables. And remember that we have an algebra, I don't remember how I call, remember I assume that I have an homomorphism from R to, okay. Let me, yeah, okay, that I assume to, okay, let me write this simpler, that I assume to have an embedding of the algebra of continuous function inside the sister algebra, okay? Then the Schwinger function depended only of this algebra, okay? But I can make, okay, I can make, so acts as, I can make this algebra act as multiplication operator, okay? So I give a representation of this algebra, that is, I say, okay, I say, I don't know what, okay, let me use just, I don't want, okay, let me, so I have this representation of the algebra, okay, so, and this simply acts as a multiplication operator with x0. So remember, these are functions. So I define on the, let me define it this way. Okay, so this is the key point. Okay, so this algebra is an algebra function of R. So you evaluate the process in 0, then you multiply, you get a bounded random variable, and then you can multiply the f. Okay, so this is so let me maybe triangle. So to put some points, then we have the algebra of observable, and of course you can check that this is C star homomorphism. Okay, so respect the algebraic properties. And then you have an additional, so now you can introduce an additional operation. Remember, we have to, so what we have to recover, okay? So we had the Hilbert space, then we have the representation of the sister algebra. And my Schwinger function, so I decided at some point that I don't look at all the elements in the sister algebra. I look at particular abelian subalgebra, which I assume to be just this algebra, okay, the algebra of continuous function in some on R. And then I act with the semigroup K. Okay, this is already in the Euclidean context. Okay, so somehow I need to recover this semigroup, and here you have okay, you look how it was defined in terms of Schwinger function, and actually here you can express it. You can express it precisely. So remember that yeah, let me, first of all, we have an actual action of time translation. Okay, so time translation can act with positive times. Okay, so I can introduce certain operator x star tt, which act on this function, E plus, so my Hilbert space, by shifting time positive time. Of course, you can imagine that you do for functions of this form, you just shift all the times. Okay, and that's fine. Okay, you cannot do for all times. Okay, you cannot define it for negative times because this function, the Hilbert space, is somehow it's only made of function of the completion of function which depends only on positive times. Okay, so if you want to introduce a time shift, you have only one choice. You have to shift in one direction to stay into the space. Okay, and then this time shift acts on E plus. Okay, and this starts to be what we want to do. Okay, and essentially this is the semigroup. Okay. But so let's see what does it give us. No, so now the next observation, okay, important observation, the elements of the form f minus conditional expectation of f with respect to f0 so these elements have 0 norm. And you can check directly. It's okay. It follows from okay, exercise if you want. That's maybe it's useful to do it. Okay, try to do it yourself. If you don't manage, maybe we can discuss, but that's not difficult. And in the extended note, I wrote the proof, but really, as soon as you just write it down and then use the Markov property. I think maybe you have also to use the symmetry, but I don't. Okay, So all these elements are in the null space N. Okay, so as far as the Hilbert space structure is concerned, you can replace any vector by the conditional expectation with respect to F0. So only what happens at M0 matters. That's what this says. Okay. And then, okay, so this is, okay. So let me order in the way maybe I want to say. So you have this property, and then, no, sorry, I copied twice the same. Next property is that, so T is a symmetric operator. Okay, let's see how does it work. So you have two functions. So what is this? Okay, I just copy the scalar product, and this is TT. So I want to prove that it's symmetric, okay, that it goes on the other side. So now what you do? Well, I can use time translation invariance to rewrite this as the translation of all, okay? The translation applied to all together. Of course, I have to go translate back this first part, for example. Okay. And then the law, it's time invariant, translation invariant. So this first thing disappears because the law, it's invariant under translation. So if you take the average here or there, it's the same. Okay. And of course, you have this. And now, when you take it inside, you have to remember that this is doing the time reflection. So translating of minus t, it's equivalent to translating t of t, okay? And therefore you get what you want, okay? So what I used, okay? I used by stationary of the law. So this I use here, the stationarity of the law, and then here I used, okay, the definition of theta, what I used else, and the definition of theta, okay? And the definition of theta, if you want, okay? I didn't use very much. This also implies that T, so if you take a vector in N, you get another vector in N, sorry. Okay, because you see if G is in N, then somehow this scalar product is 0. Sorry, if G in N, then this scalar product is 0. It means that this is 0 for every f, but of course this means also that it's 0 for Tg, so the norm is 0. Okay, so the symmetry implies that the null vector are preserved. And now we want to prove that we want to show that Tn is contractive. Okay, so this will really be our contractive operator. Okay. Okay, so I want to show that it does not increase the norm of a vector. So this is T, the norm of Tf. And I can use the symmetry and the semigroup. So I use the symmetry to put it there. And then I use the semigroup property, okay, to get 2. And okay, and then I can bound. So this is a scalar product. So I can bound with Cauchy's vars. Okay. So this is in this Hilbert space. Okay. You have to pay attention because there are many Hilbert space around. Okay. For example, you have the L2 space of the probability measure, but that's not the scalar product. Okay. This is not the same. And then here I have T2 ta F. Okay, and again in H. Sorry, yeah. yes, I think I'm fine. And then did, okay, so indeed I'm iterating. We have, now you iterate this inequality. So what you have, so let me write TF here. So what happens when you iterate? So maybe, let me see, maybe it's easier to write in this way. So you, or not. I think I made an error. No, I think I'm right. So you have this, then you iterate. So you can iterate, okay? You have TF and then you iterate again many times. So, and what you get, so you get something like this, okay? When you iterate, so every time you leave behind the norm of f, and this increase by a power of 2, and you get this powers of n. And then you can prove that this converges to just the norm of f, okay? Since, so now to prove this, of course, this converges to 1. So this is, you have to bound this guy, okay? You have to prove that this is not growing, okay? Which is not clear because, okay, this exponent is getting smaller and smaller, but this time it's getting larger and larger, okay? But you have a uniform, bound for this quantity, and this bound comes from the other L2 norm, okay? So let's see what is this guy. So this guy, you can write it as, so this is the definition, okay? So I didn't write the definition. So in the definition, this T is inside, but you can take it outside. And then you can use the, okay, here you can do whatever, you can, now I want to get rid of this dependence on, sorry, I forget T here. Just need to, I want to get rid of this dependence on T. And what I can say is that I can use the Cauchy-Schwarz inequality, but with respect to this expectation, okay? So now, so let me write in this way to be clear what I'm doing here. So I'm using another structure. I'm not using what I've done before, okay? This is not very good to prove that it's contractive, because I want the contractivity with respect to this H norm, not with respect to the natural L2 norm of the Hilbert space, but of the probability space. But you can use that structure. Okay, so you see here, our assumption that we are in a probability space give us this. Okay, and then you are done, because so you see this is the translation. As soon as you write like this, these are the translations of this function. Okay, you can take the translation outside. Of course, the translation acts pointwise, so you just translate everything. And then you use the time translation invariance of the process to just get rid of all these translations. Okay, and this is okay. This is finite. You can assume that this is finite, and this means that this is finite uniformly in T. Okay, and then this justifies this last step here. Okay. But this is not useful by itself. Just want to remark, because somehow you don't respect the Hilbert space structure. So you have just really to couple these two arguments. But then, okay, you have this condition. Now let me comment that in general, if you don't know that you are in a probability space like this, you have to use this analytic condition I spoke about with respect to the Schwinger function. That is, the analytic condition, it's really encoding the fact that the semigroup is a contraction semigroup. Okay, so now we are proved. So we have proved that, okay, norm, okay, if you want the norm of TF, TT is bounded by 1. Okay. And then, okay, then just the last step is the strong continuity of this semi-group follows from the approximation, okay, from the weak continuity, from the fact that we use a continuous process. It would be enough that it's continuous in distribution, okay? So the operator is bounded, so essentially you can reduce your considerations to like cylinder functions, and then for cylinder function you can just use that the n-dimensional distribution are continuous in the time parameters. That's not difficult at that point. Okay, it's really natural. Okay, so we are in a good position, and essentially we have reconstructed our data. Okay, we have also the ground state. Okay. The ground state phi is given by just the function 1, okay? Indeed, for the function 1, you have that the semi-group just send 1 to 1, okay? So actually the norm is 1, okay? So this function, and this also show that. So the norm of the operator is really 1. Okay, it's actually not smaller than 1. Okay, so we have reconstructed. We have constructed, if you want, an Hilbert space. Let me make the point, okay? And let me call star homeomorphism in the sense. Okay, let me introduce some notation which maybe I didn't introduce before. Let me call it Q of A, okay, not pi of A. So this is still a star homomorphism, okay? Star homomorphism, but it somehow, it will be meaningful later on, okay? Q from C over C into the bounded operator over H, and a semi-group of is a strongly continuous semi-group T, okay, which is what I had there, okay. Okay, then you essentially you have all the data. So now from this you can recover so just abstractly from which we can recover, remember, from which we can recover a unitary group UT, okay? So that's abstract. And another homomorphism, stereomorphism. Sorry. Yeah, let me give I'm not sure. Let me give a name E to that one, just to, or I don't want to call it X because X here it's the process. So let me give another name. Okay, let me call it. Can I call it H? Yeah, let me call it H. Okay, and H is the same. So it's another star homeomorphism, and such that. Remember, okay. So what was this? This is what it was, homeomorphism, where you give it the complex exponential. Okay, it gives back UT, and when you give it, so it contains the information you encoded in the semi-group. When you give it the real exponential, it gives you K. Okay, okay, so somehow you can, and this already repeated many times, but as soon as you have, sorry, you have this semigroup, so actually this is CT in this case, okay? So I just changed the name to the contraction semigroup, but somehow these three objects encode the same information, okay? So recover, actually you are positive, positive energy. Yeah, so this was the condition, okay? The contraction semigroup, I told you yesterday, correspond to a positive energy unitary group, and the homomorphism actually take value in the continuous function on the positive real number, okay? That's the positive energy condition, okay? And remember that we use this to go from the unitary group to the semigroup, okay? So this for T in R, and this for T positive. But they are not, like one is the imaginary time and the other is the real time. Okay, so we solved so somehow this shows how you solve the problem. Okay, you go back, you have an Hilbert space which contains, which can represent all the states or the somehow the interesting states of your system, let me say in this way. Then you have observables, okay, because for any function of R, you have an operator, and you can reconstruct really the expectation we wanted to measure, okay? So the stochastic process contains all this information, okay? Not in a trivial way, but it contains it. So let me be more specific, okay? So what is this Hilbert space H concretely? So this is the next question, okay? I want just to pause a moment, maybe up to the end of the hour, to discuss, so how can I represent it easily, okay? Or, because somehow I told you, okay, this mod out of this zero vector, it's very strange. It seems modding out a lot of things, okay? Any vector of the form F minus conditional expectation at zero norm. Okay, so it means you can replace any function of this form with its conditional expectation, which in particular depends only on what happens at time zero. Okay. Yeah, let me be more precise. Okay, in this point, just to clarify to you what does it mean. Okay, in particular for cylinder function. Just to have because I want to have an intuition. Okay, so imagine you have a cylinder function. So a cylinder function like this, F equal like this, is equivalent in the Hilbert space, okay, that is modulo zero norm vector, to its conditional expectation, okay? And what is its conditional expectation? Well, okay, you need just to take this conditional expectation, sorry, of that guy. Yeah. And this actually, you see, how does it look like? Well, this is a Markov process. Sorry, this is not even F0, but it's equivalent, okay? Because of course that's only. So what you have? Well, you have this, and then now, yeah, this is a function. So let me call, I'm not sure if it's very useful here, but this is PTK. Okay, so you see, you go from time 0 to time k, and then you take this exponential function. So it's for you, if you know something about Markov process, you could say, okay, this is just this. Okay, so where PT is the transition operator of the Markov process. Okay, you could imagine that any Markov process with the property I told you satisfied, it has a transition operator which tells you what is how, okay, you have a function and it takes you the average of the function with respect to the process given that you start the process at time in x. Okay, let me just write formally like this. Okay, so this tells you what is the probability to go from one point to another in a given time. So you see all these functions, so this tells you yeah, actually, I think okay, so let me take so all any function in the Hilbert space is essentially equivalent to a function which depends only on the initial point. Okay, because you can mod out you can project, and the projection just remove the null vectors. Okay, so you see, so this tells us something something about the function. So let me go back. Ah, sorry, I didn't. So I had the question. An equal sign is missing. Sorry, Vlada, where? Now I'm lost.
It was missing, but
okay,
in
yeah.
the meantime, you put it.
Yeah, thank you a lot. Good. Okay, so I'm going back. Yeah, the only problem with this way of working is that you have to follow what I'm doing. So please let me know if you want to look a bit more what I'm writing so that I can stop in some expression. I didn't find any solution for this problem yet. So by the above consideration, by what we saw above, so above, we know that we can replace any vector with its projection onto the x0 sigma algebra, onto sigma x0. Okay, that is any vector is just a function of, okay, measure a function of x0. Okay. So what we have, so let me, so you have, so you have this idea, okay, you take two vector, then, okay, here I prove to you that you can project and you get the same value, but what is this, okay? So this does not contain anything, okay? Just telling you, okay, this scalar product is this, then you project, but what is this, okay? This you can rewrite in the probability space is some function. Of course, this is measurable with respect to x0, so it's some function of x0 times some function of g0, and then you see that this depends only on the law at time 0, which I called rho, okay? Where rho is the law of x0, and actually at any time, okay, because the process is stationary, okay? So you see really what is this Hilbert space now, okay? This is, you can recognize this scalar product, okay? So this Hilbert space, it's really the same thing as the L2 over R with the remeasure rho, okay? Because you see you have this, yeah, and F is, Fg are functions, okay? Functions representative, so that they're not unique, but anyway, you're just looking at the Hilbert space structure, so you don't care about the ambiguity because it's measured 0. Okay, so we learned this at this point. So this Hilbert space, it's a very familiar. You can represent isometrically as the L2 space of some probability measure over R. Okay, and QF of, sorry, now QA of F. So how does the operator Q acts? Very simply. Okay, so QA of X acts as just multiplication. Okay, because I remember that Q was acting as multiplication with time 0, with the time 0 feed. So let me go back. So I remember to you how was acting Q. Okay, Q was acting just multiplying time 0. So when you take the conditional expectation, it just remains the same operator. Okay, so you have the observable acts as multiplication in the variable, as you would expect. What else? What happens to the semigroup? Okay, but but the action of T is more complicated, okay? In this representation. Because T was translating the path, okay? Now I'm projecting back to the algebra times 0, okay? Indeed. You can always, you can take, of course, okay, you can, what is this? This is now, so if you take this random variable, this will be f of xt, and then, and now you have to project back now, okay? Tt of f is equivalent to the condition expectation. I told you that you can replace everything with the condition expectation, okay? So this is like Pt of f, okay, as I defined before, actually. So you see that what was the translation operator in the path space become the transition kernel in this representation, okay? Okay, so we have, okay, yeah, I call it K, let me call it K. Yeah, KT, yeah, this is it's the same operator, okay, but you are somehow modding out the part you don't like, and I told you that, okay, the Hilbert space it's really L2, so in L2 you represent as a how I represent this operator as a function. It acts on, let's say, L2. I'm a bit, please, if you are confused, let me know, okay? I should write this isomorphism back and forth, but I don't like. So on if you look in this representation, what happens? Well, it has a semigroup, KT, let me give it a name, so KT. As a semigroup, and this semigroup, so it should depend on function of only a real real number. And how does it look like? Well, it look like what you expect. Okay, it's just Pt of f, and x is real. Okay, actually, it's in the support of. You can take it like this. Okay. Yeah, I think this is what I wanted to say. Okay. Okay, if you don't understand what I'm saying, you just indeed remark that. Okay, what I proved here is that if you have TT, okay, if you have two vectors and you have this, then this is in this other vector space is equal to KT. Okay, so you have isomorphism between these two structures because you respect all the scalar products. Okay, so this operator. Okay, yeah. Okay, this is, I think I'm in a good position, I hope. Yeah, so you see, you have constructed, yeah, here in this, so in this further section, what I showed to you is that somehow this Hilbert space, which looks very large because you started with somehow a process depending on all times. After this completion and modding out the null vector become really small. Okay, now everything just happened at time 0, and the only things which remember that you had a process was that now you carry on. This semigroup is really the semigroup of the process, okay, in this language. Okay, and again, okay, that's contraction semigroup, so it encodes the dynamics in this Hilbert space. Okay, so how it encodes these dynamics, apart from the abstract way of reconstructing the unitary group, I don't have in general more insight. Okay, I have to consider very specific examples. Okay. Okay, yeah. So then I made I made this remark that this seems very nice and very easy, and you see, I reconstructed everything with without even talking about somehow Schwinger function and Weidmann function, and why all this. You could even forget about reflection positivity if you like. Okay, if you have a Markov process, there is no. Okay, if you have a Markov process, you know, I proved to you that this object is positive. So for any symmetric Markov process, you can always do this recipe I explained to you this morning. Okay, you don't have even to imagine that reflection positivity is a notion worth of a name, because you just write down this object and it's you prove that it's a scalar product. That it's the right object is because it gives you interesting dynamic. Okay, if you use, yeah, that's interesting. You know, you can use, what happens if you use the L2 scalar product of the probability space. Okay, let's ask this question, because it makes, so this is where somehow you are encoding everything. Okay, it's in this choice of the scalar product. I could have chosen the scalar product of the probability space, that is not put this theta here. What happens if you don't put the theta? Well, you have still observables. Yeah, you could. This, first of all, is not a contraction semigroup anymore. You could. It's actually a unitary group, because you can go back somehow. Okay, depends if you take this function or not. Let me think. What happens if you take the other scalar product? Yeah, so somehow some of this consideration should not work. I don't, now I cannot recollect what happens. Maybe I don't want even to spend too much time on that, but yeah, think about it. I will think myself also. Okay, just to say, you could use another choice, but it will not work. Okay, and now I don't remember why. Yeah, the T become an isometry actually in the other scalar product. Okay, and yeah, I don't remember now what to say actually about this, but okay, think about it anyway. Of course, in the other scalar product, you really don't have this reduction. Oh yeah, that's already an interesting point. Okay, if you use the other scalar product, you don't have this reduction, drastic reduction. Okay, because then this argument with the argument I left you as an exercise does not work anymore. Okay, this argument does not work. Okay, it's clear that L2 space of all the path space is not equivalent to the L2 space of the at the time zero situation. Okay, yeah, let me not spend too much time here. I want to progress, unless you have question on this part. Now I give an example. Okay, so the next subsection, an explicit example. Explicit. Yeah, maybe, okay, an explicit example. Okay, so the example I want to take, so let's take the OU process. Okay, yeah, the Gaussian process. Okay, there are many OU processes, but we take the simplest one. Okay, we take a real Gaussian process defined for all R with covariance. Centered Gaussian process with covariance. Okay, GT exponential minus alpha, I called. Okay, so this is just very simple. Okay, with alpha positive. Okay, alpha is a fixed parameter, and this is a Markov process, a symmetric Markov process. Yes, so you could, it also solves the SDE. So I talk about, yeah, very briefly, actually, maybe not at all, about SD. So if you look at this Markov process, you can, yeah, you can prove that you have a Brownian motion, and or you can represent as the solution of an SD. Let me say in this way, okay? And the initial condition or the condition at any time is given by, so it's the stationary solution such that, let's say, at any time you have low normal Gaussian with this covariance. You see from here, if you put time 0, you get 1/2 alpha. And it's solved where B is a standard Brownian motion. Now, I think I'm wrong here. So somebody maybe can correct me. Here, I always get the normalization wrong, but yeah, now I think with this normalization, everything is fine. Okay, if you have 2 alpha here, then you have a standard Brownian motion. If you don't very much about SD, we would not use very much stochastic calculus in this lecture. So just imagine that you can solve. Actually, I can maybe, yeah, I mean, that's an information I need later on, okay? But it's a standard fact, probability theory that the Austen-Uhlenbeck process is the process which satisfies this equation, and it has this covariance. If I didn't, if I got my normalization rights, okay? And you can check out the properties. Let me see what I want, because in the notes I put some more details, but for the moment I don't, essentially it's not an information I need. Yeah, I want to find, yeah, I need to find the transition kernel. So now I gave the process, okay? I told you also that it's a symmetric Markov process. We know that it's reflection positive, but actually we will also know that it's reflection positive as soon as you know that it's a symmetric Markov process. Now, what is interesting now, it's how looks like this K, okay? K is the transition function, okay? So we can compute its transition. We can compute its transition function, okay? It's a Gaussian process, so you know everything. It's you can solve even the SDE. There are many ways to compute the transition function, so let me not maybe leave you as an exercise, try to do it. So, but the transition function was easy. So somehow you have to compute f of x, given that the initial condition is x, okay? The condition at time 0 is x. So this is the transition function, and I have an expression which maybe will be useful later on, so let me write it explicitly. It's the transition function, it's given by an expression of this form, okay, where z is a normal random variable, okay? That's a convenient way for me to write this transition function, okay? You can prove it in many ways, and in the notes I put some way, but maybe think about yourself. T is positive, I think it's well known. So, so you see, it's like, okay, it's what it's written here. I don't want to comment too much about it. Okay, you take the function, you put the initial condition get depressed by this factor. Okay, at time 0 it's x, and there is nothing else. Then as time goes by, the initial condition is depressed, and then you get more and more randomness inside, and when time goes to infinity, this goes to 0 and this goes to exactly the invariant flow. Okay, not, yeah, this I didn't say it before, but it's true in general, that is kt of f converge to the mean of f, so the integral of f with respect to the rho as t goes to infinity. Okay, and this actually this happen in the general context too. And okay, convergence you have in L2, but of course, if you look at this formula, you have even a stronger notion of convergence here. Okay, so now in this example, what I want to do in this example, I can perform explicitly the construction of U and Q. Okay, so U and Q, remember, U is the unitary group and Q is the homomorphism which encode both K and U. Okay. And okay, you check that it's strongly continuous. Okay, that's one can check. Okay, but strong continuity somehow it's clear as soon as, for example, you know that the Oster-Uhlenbeck process is a continuous path. It's continuous path, so we are in the framework above. I can perform, yeah, so let's do it. So that's what the next thing I want to do. So in general, okay, it's complicated, but in this example, it's easy because actually I can diagonalize, okay, we can diagonalize, okay. Okay, so it's very easy, of course, maybe you already know, but I think, remember, okay, the Hilbert space, sorry, I didn't say what is the measure mu. Sorry, in this example, so the measure mu is essentially this, okay? So the measure mu, it's this Gaussian, okay? Sorry, the measure rho, the law at time 0, is that one. So rho is the Gaussian, okay? So the L2 space in the previous paragraph is the Gaussian space with these variants. And then we have K, we have the algebra of multiplication operator. Then I want to find U. What is the unitary group in this example? You could guess from this formula, okay, but actually maybe not because one has to take, okay, let's not do it like this. Okay, let's diagonalize K. And to diagonalize K, I need a trick, but somehow we will do some computation which will help us later on. Okay, so these are some Gaussian computations which are useful to have a feeling what will go on when we consider more complicated Gaussian processes. So let's see, take maybe E of lambda now. Okay, E of lambda of X, we take this particular, E, okay, just take the trigonometric exponential, okay? Then what happens if you give to lambda? To K, sorry. And okay, you have the explicit formula, okay? But of course, this is a complex exponential, so there is a part which go out and a part which you can compute explicitly, okay? It's just the characteristic function of a Gaussian, okay? So you get something like this, okay? This part go out and you have this, okay? So you get a more or less the same function, but not quite. But then you think a moment you can change lambda, okay? So that to reabsorb this factor, actually. So the conclusion of this part is that, so you can reabsorb and you have this factor, but if you somehow share this factor on the left and on the right, it's a constant. You can derive that if you take these slightly changed functions, okay, if I multiply just, so this I call E hat, and I compensate a bit with a factor, but it's a constant, but this make the formula appear nicer because you see that now, okay, somehow this family of function is kept invariant by the by the KT, okay? So you could say, actually, let me remove this. We have this, okay? And this tells us something because you can expand both sides in powers of lambda, and okay, you would have to prove that you can really do this operation, okay? But with explicit form and with the property of the Gaussian, it's not difficult to check that you can really exchange the sum and the integral. At least you can do in power, and then you can check, you can, okay, so you have equivalence of these two series. And then you see something here, which is very interesting, okay? So the coefficient has to be the same, so this has to be equal to that, okay? So we learned, okay, we learned something interesting, that somehow these coefficients which appear in this expansion are eigenfunctions of K, okay? So these are polynomials, are eigenfunction of KT, okay? Hermite, okay, they are called Hermite polynomials. I'm not sure. I'm not sure they are properly normalized for what is the definition. So I will just use. Okay, they are normalized according to that. Okay, they're really the coefficient in the expansion of the exponential of this modified exponential. Okay, they are the coefficients in the series of this quantity, okay? So just to record this property, so so you don't just take the complex exponential, you take this strange exponential, and you say they are the coefficients in this expansion. Okay, they are defined combinatorically by this formula. Okay, so this is so we have diagonal, so end result of this computation, we have diagonalized the operator K, okay? Okay, so we have a lot of information about this, okay? So since K T is symmetric, this means then the Hn are orthogonal, okay? Okay, they correspond to different eigenvalues, so they are orthogonal. Okay, then it's also, yeah, sorry, I need also that they are orthogonal and actually a basis for L2 of rho. Okay, so this is, remember, it's the Hilbert space essentially. Since, yeah, since if you have something which is orthogonal to everything, okay, let me, so why it's a basis, so you can check such that, so imagine you have a vector which is orthogonal to each of them. So what is this, okay? Imagine that you have a vector which is orthogonal to any of them, but for all n, this implies, okay, since it holds for all n, and you have this formula, then somehow it holds also for the, it holds for the exponential, okay? So you have actually that it's 0 also for the exponential, okay? Because for every coefficient it's 0. And yeah, this function are in L2, sorry, I was a bit confused. And then this is a matter of Fourier transform, okay? This is, okay, these are now trigonometric functions, and you can approximate f and the functions, and okay, you have this for all lambda real, and somehow now you have various ways to conclude that the function f has to be 0, okay? by density, you can approximate with continuous functions, and then somehow this is telling you that the Fourier transform of this function. Okay, but continuous nice function, and then Fourier transform is 0. Okay, and you can reason in various ways. Okay, or by constructing using the exponential to construct a dense subspace of the Hilbert space by essentially by density. Approximation. Whatever. Okay. Yeah. So I have a question. Maybe. Aren't we missing any alpha in the right-hand side? Yeah. Thanks for this remark. Yeah, we are missing alpha, but yeah, I've been a bit sloppy here. You're right. So we leave implicit. So that's an important remark. Thanks. The dependence on alpha. Okay, so actually this polynomial depends on alpha because I'm not using the standard Gaussian to normalize them. And I was a bit lazy to recover the exact normalization. Okay, if you want, define them with alpha equal 1, and then you have just to think a bit how you go on to put alpha around. But essentially, there will be alpha inside and alphas outside. But okay, for the moment, I don't need this. So let's leave implicit, or if you are bored, sorry, if you are bothered by that, just think alpha is equal 1 in this consideration. Okay, it's not very, alpha it's any number, and by rescaling things, space and time, you can get alpha equal 1. Okay, if you rescale time, you get alpha equal 1 here. And if you rescale space, you get alpha equal 1 in the measure. So then you can recover things, sorry. So yeah, I just wanted to give you the structural properties. Okay, maybe even some of you are both annoyed, but somehow I like, I mean, this is very well-known facts, okay? But somehow for many of you, which maybe are coming from more PD side, they don't know this, or they don't keep in mind. So I would need something about this Hermite polynomial later on. So it's nice to get some of the theory now at this point, okay? So I have this. Okay, then you essentially it's a basis of L2. Okay, it's a very nice basis because I can diagonalize KT, and then at this point we construct easily both Q and U. Indeed, okay. You can imagine how they looks like, okay? We have diagonalized everything, so now the problem is becoming unidimensional. So what is Q of a function A? So let's apply to Hn x. Okay, Q, sorry, not Q, I wanted E. E is just, you see, he has to be such that when you apply to, it to the exponential, you get this function. Okay, so it's just alpha f of alpha n. Sorry, f of a n, because this is the function a. Is a function on R, and you compute in this way on the Hermite polynomial. Okay, and u of t will be. Now it's just the same thing with the complex exponential. And they satisfy the properties I told you. Okay, so they are unique. Okay, because they satisfy the property I told you, and you can define on a basis. So actually, I don't need H here. Okay. So they are defined, and then you check they satisfy the property, okay? In E, if you put here the complex exponential, you get that. If you put the exponential, you get that. And and then they have somehow the continuity property you expect. Okay, so this solves the problem, okay? This is the dynamics now in these variables, of course. Okay, so this solved the quantum mechanical problem in this very simple model. Okay, I have everything. I have an Hilbert space. I have a representation of CR. So this was Q. And a strongly continuous dynamical group U. Okay, and actually I have this additional representation. Okay. And now you see something here. So the isomorphism only care about the values. Now we'll see that E only cares about the value of the function A. Sorry, U of A. So a priori the function I took I knew that it was positive. Okay, remember on the set alpha n. Okay. Okay, so any function you put here, you get the same thing. Okay, so this actually means that this quantity, so this observable is quantized. Okay, you just you only observe these numbers. Because you can modify the function outside and you get the same measurement. So essentially, you can imagine that you can just if you take a function supported not in the set of these numbers, then you get zero. Okay, that's the measurement. It's always zero. So you will never see anything in that interval. Okay, so that's how you can say that. Okay. Okay, so it is actually homomorphism from okay, the continuous function on the discrete set, which is just okay, you can just a sequence of numbers, okay, with the supremum number. Okay, the quantity E is quantized. Can only take quantized. Can only take discrete values. Okay, it's supported only in a discrete set. Moreover, E of A is constant in time. Okay, meaning that okay, you can check that if you take the time evolution of E of A, which was defined in this way. Sorry, maybe I should not. Yeah, okay. Yeah, let me call it in this way. This is E of A. Okay, so these are quantities which are constant and quantized, okay, and actually correspond to the energy. It is a constant motion, and actually it is the energy, okay, of course. It is the energy. Okay, but I didn't want to use the, so if you know quantum mechanics, you see that I'm trying to work hard and not to use the language. And why I wanted to avoid, because I wanted to have a logical, a framework, conceptual framework, which, so when you explain usual introduction to quantum mechanics, you have to understand the correspondence to classical mechanics. Okay, then in classical mechanics, you have concepts like energy, position, momentum, and then you introduce Heisenberg relation, commutation relation, all these things, okay? And this makes very difficult, as far as in my experience, to explain this to master students in mathematics, okay? Because they don't know classical mechanics, and they don't know certainly Hamiltonian mechanics. So all these concepts are very, very far from their intuition. And then I somehow, yeah, in this way of presenting the things, you'd never need these concepts, okay? And this is why I'm trying to work hard to go around them, because I want to see how far you can go without introducing this like metaphysics of how you interpret these things, okay? So I tried to have this, not to introduce too many language or metaphysical entity, okay, like the energy, okay? In this context, the dynamics produce somehow this observable from, you see, time we understand, and then we understand, I try to explain to you that we have a dynamics which keeps this somehow, which is an automorphism because the system does not change shape during the time. So you have to relate observable at one time to another time to be able to relate observable at different times. And this somehow creates this, this entity which is related to the flow of time in such a way that it is constant in the flow of time. Okay, it's a constant of motion in the quantum sense. But of course, if everything would be commutative, it would be like the standard constant of motion. Okay. For us, it's not very important. Okay, in our formalization, we just care about the U because this gives the automorphism of the sister algebra. And I just note that somehow we have this additional quantity. So let me remark, so let me now make the following observation that, you see, we started with a probabilistic model and we end up with, okay, an Hilbert space. On the Hilbert space, there is the representation Q, which is, so, but it's a family of commutative operators. Okay, because the algebra CR is commutative. However, the dynamical group does not commute with Q. Okay, I mean, you see here. Okay, does not commute. Okay, it's really doing something to the various components. Okay, if you apply to if you commute it with a function, it does not give you back the same function. Okay. Okay, maybe check. Okay, show exercise. So show that QA and EA do not commute. Oh, sorry, QA and AB do not commute for any. Okay, you take functions. Okay. It seems a strange language, but that's the only language you can use if you don't want to work with unbounded operators, okay? Because somehow, of course, both these homomorphisms are linked to two unbounded operators. The first one is multiplication with X, and the other one is multiplication with N, okay, which are unbounded. So if you don't want to discuss unbounded operator, you have to work in this language. Okay, so you take two functions, and you need to show that these two operators do not commute, okay? For any function, okay, actually. But yeah, it's okay, just try to understand they don't commute, okay? So actually, you see, we have an algebra which is richer than just the algebra of Q. We have another algebra which interact in a strange way because they don't commute. So the dynamics encode the non-commutativity in this problem, okay? And again, okay, we started, all this is inside, somehow encoded inside the Oster-Uhlenbeck, the usual Oster-Uhlenbeck process, okay? So let me do what I want to do. I think I have still, yeah, I think I need some, let me see. I think I prepared some computations, but maybe I don't need them now. I will put them in the, so I wanted to show somehow that actually this energy, what you expect from the harmonic oscillator, and that you have commutation relation, but maybe I don't really need it now. So let me just skip this additional part, and I will put in the notes. Okay, so I said somehow this message about the non-commutativity, yeah. So I wanted to point out, okay, okay, let me just maybe wrap up this part and showing you how you use all this to go back to our problem, and think about so how we use all this to solve the original problem. Yeah, compute average, compute results of measurement. So that was where I started. Okay, so so now we have so now I have a state. So I imagine I have my system in the vacuum state. Okay, the state corresponding to the vector 1. Okay, so that's the vector in my Hilbert space. It's 1 because my Hilbert space, remember, is just L2 of rho. And so 1, it's element in L2 of the Gaussian. And then imagine you want to compute now something, okay? You have an observable. And again, okay, maybe I insist, maybe I wanted to make also the point that it should be more correct from the conceptual point of view, just not to look at products, because somehow you cannot measure products of two observable at different times, okay? That's not, remember that in our interpretation as a measuring things, you don't have this non-commutative product, okay? The only thing you have at the origin was this Jordan algebra product, okay? So this is what you want to measure, okay? This I explained to you what does it mean, okay? You have an apparatus at time 0, then you have the same apparatus, but you just measure at time t, or you could measure another thing. And then I explained to you what is this, how you measure this, okay? That was clear. And there is no, because if you write the non-commutative product, then you have you have to interpret, okay, what I see in the laboratory is alpha t a times a, or the other way around. And actually it's neither, okay, because somehow in the kind of formalization we wanted to give, we have only the right to use at the end of the day the Jordan algebra product, okay, and which is the symmetrized version of the sister algebra product. Okay, remember the sister algebra does not, we could not motivate. I don't know how to motivate it. I just use it because I choose it. That's arbitrary, one of the many arbitrary assumptions I made along the way. But somehow at the end of the day, you have to measure this. So this is what we want to measure. Now the point is that we are at a point where I can give a number out of this object, essentially, okay? Because of course I didn't tell you what is the observable. But this you can compute, okay? So is the symmetric part. So actually you then, I think I made the computation correctly, maybe. Okay, maybe I'm wrong or not. Okay, anyway, should look like something like this. So this is the ground state, it's 1. And then you apply A, and then you apply this other thing, or in the others, or in the other direction. Now I could have made a mistake anyway. So actually, let me use my correct notation. So I use a representation which I called Q. So actually I should write in this way. Let me just correct what I was writing. Okay, and then you can okay, then you can perform this. Now you know everything, and you can perform this computation. You know the dynamics. You know, and how you do this computation. Well, you diagonalize. You essentially you applied this u. You can put on the other side, and disappears. So you remain only with the one u, so this disappears because it applied to one, which is constant, and then you have only one u, of course. And now you just put a resolution of identity somewhere here or there, which is made by the basis Hn, so you get just an expression like this. And then this is that, okay? Okay, so that's okay. If you give me the observable, I can measure it. Okay. So I constructed a quantum model. So I constructed a model, a probabilistic model. From this probabilistic model, I went to the corresponding. I constructed a quantum model out of it, and this quantum model gives me numbers out at the end of the day. Okay, and then I need to compare this number with the experiment. So I need somehow to guess what is my experimental setup, how correspond to A. And I need to measure the same thing twice after some time. And then I can ask a meaningful question, that is this model corresponding to my experiment or not? Okay, the answer could be yes or no, but if it's yes, then I could say, okay, then I have a quantum mechanical representation of this physical phenomenon. And then I can make other experiments to check other properties, okay? For example, here you see that it says something very specific, okay? This you can measure, it's a function of time, so you can decompose in Fourier frequency, and you will see that if the model coincide, I mean, this model make already a prediction, okay? That if you take the Fourier analysis of your measurements, then you should see only discrete frequency proportional to this coefficient alpha. Okay, so you can measure alpha. You can check the hypothesis that in your system, that your system is described in this way. Okay, that was okay. So in this system, one observe only frequencies of the form alpha n. Okay, let me say in this way. Yeah, so all the harmonics of alpha, if you want. I'm not sure. Okay, so that's a prediction of this model. Okay, so this model either it's correct or not, but okay, if you observe in nature this kind of phenomena, that is your system seems to have quantized frequencies, then maybe that's way to represent it. And if you do further experiment, you check other hypotheses. So that's somehow to me it's this concluded example. Okay, so I arrived at a point where I started with a probabilistic model, and we arrived at number which you can check really within nature. Okay. Okay, so let me go on in the last...
I have a question.
Yeah, please.
So in this formula, we compute the average measurement results.
Yeah.
How can we see the probabilities of each of these outcomes? Can we see it from this formula?
So, okay. So the point is, what is the probability? So in the real world, you don't measure probability. No, you measure only frequency. So what you do is that you repeat your experiment, and then you measure the average. Okay, so anyway you measure all these kind of things. These are averages. So in particular, if you take this A to looks like a characteristic function, this would give you probabilities. Okay. For example, I didn't insist much, but of course this is a multiplication operator. So A has to be a bounded function, so I cannot really match the H. Okay, but I can simplify this formula. So let me. So you can do something, no? Like you can take your function, sorry, you can take this Q of A of 1 to approximate Hn for some n, okay? Then somehow this tells you in this, if you then want to have a metaphysics of particles and things like this, then this formula tells you how you create, how you construct a measurement apparatus which create n particles. So somehow this formula is telling you, if you interpret with all the metaphysics of quantum mechanics, that from the vacuum you can create, this is telling you, okay, from the vacuum your measurement apparatus perturb the system and it can create any number of particles. Then these particles propagate and they are reabsorbed by the same apparatus after some time. And the fact that you have these frequencies, somehow you interpret saying that the particle does not do anything in time, okay? They just sit there and oscillate, and that you have particle is because you have a discrete number of them. So this system is a boson, is a one-dimensional boson, okay? Describe something where you can have one particle, two particle, three particle, and if there are three particles there, they stay there forever. They don't move, they don't do anything unless you measure. When you measure, it perturbs, okay? So you can give an interpretation of all this which fits, because of course this is the standard formalism of quantum mechanics, but I think conceptually, for me, it's clearer to think that the only thing you can measure is this. All the other interpretation you put, it's formalism. So I had another question here. So there is both alpha in the evolution group and in the equation, and in the SD is on purpose. Well, I didn't have any choice. Of course, it's related. Okay, so this alpha here, if you want, this alpha here is this alpha here, and or if you want, it's this alpha here. Okay, it's this alpha. This you can change by change normalization. That's not very important. Okay, if you normalize differently your variables, that. I mean, if you normalize differently the Brunner, here you have various parameters, okay? You have essentially two parameters. I fixed only one, but this describe the dynamics somehow, okay? It tells you when alpha is large, somehow you see that the dynamics run faster somehow. Okay, so yes, so it's on purpose in the sense that I would need to change alpha later on. So I put a parameter, I didn't want to put one. I could have put one in this discussion and you would see anything. But I mean, this A, I didn't show you, but somehow the degree of non-commutativity, it's related to A in this problem, okay? So the algebra, so this commutation relation essentially are going to zero if A is sent to zero. Alpha, sorry. As far as the first question is concerned, did I answer maybe the question? I'm not sure.
Yes, thank you.
Okay. Yeah, I want to point it out this thing, no, that I mean all the metaphysics about particle that created, destroyed, they are not intrinsic to you don't measure particle at CERN, okay? You measure things like frequencies of oscillation of something, or lights, okay? Could be the light that get out and you measure the frequency. And when you decompose the spectrum, you realize that you have a very special things. And that's what created somehow quantum mechanics, as far as I understand. That is, you were measuring things in the spectrum of atomic processes, which were discrete, and no classical model based on commutative algebra of observable could describe why you get out frequencies which were quantized. Okay, that's a very vague. Okay, I'm not pretending that's the explanation, the final. Okay, but you see here that this model produces discrete frequencies, and actually it's the harmonic oscillator. But I didn't want to discuss this now. So let me go. Yeah, I think I did a bit less what I want. No, okay, no, we have this afternoon, so actually I think I'm on time. So this discuss, as told you, this and the discussion of this relation with from probability theory to quantum mechanics, okay, in one dimension, okay, in the simplest situation. And to me, it's a very compelling way to construct this is the simplest quantum mechanical model you could conceive, okay? It's apart from the free particle, which is somehow in this formalism is more complicated, because somehow the free particle, it's a particle which move without interaction, so somehow it's difficult to have this probabilistic description. Okay, I don't, this would correspond to Brownian motion, but for Brownian motion, I don't have, it's more tricky to construct a stationary version of Brownian motion, okay? Because it does not have an invariant measure. You need to use an improper measure, and yeah, okay, it's more delicate in that respect. So this is the simplest technique, and technically it's easier to do this, to do the Oster-Uhlenbeck process, than the Brownian motion. What else? What else I want to say? Nothing. So let me go on, and I want to discuss maybe 10 minutes, but I will continue this afternoon. So, okay, so we saw two classes of processes. You could hope that you can construct many other Markov process, so Gaussian process somehow are boring, because Gaussian process, I told you already that essentially they are superposition of Oster-Uhlenbeck process, and we understand very well Oster-Uhlenbeck process now. And so superposition, just the Hilbert space would be a product of Hilbert space, okay? There would be no interaction at all. So you could hope that Markov processes are more interesting, but the problem I told you is that as soon as you go in infinite dimensions, because you will need later when we discuss special relativity, you don't have easy example of Markov processes, or it's difficult to construct example of Markov processes. There exist, of course, but people realize that it's not very easy to be sure that the Markov property is satisfied. And then, so the alternative way to do, so if we cannot use Markov processes, we have to use Gaussian processes. And Gaussian processes are boring, I told you already. And we solved completely, essentially, everything you can say, because other things are just more complicated notationally, but physically there are no much more phenomenology than what I showed here. I'm oversimplifying, of course, okay, but that's somehow the ideology I want to use here. And you have to perturb in some way the Gaussian process, because otherwise they remain a bit boring. Yeah, so let me put this comment. We want to have a source of reflection positive process which are not rely on Markovianity and survive on generalization to infinite dimension, okay, which we are going to do later on. Okay, so Markovianity, we cannot use it, so we have just to fall back to just reflection positivity, because we know by the theorems I cited, so Sevade-Schrader reconstruction, that then I can go back only with reflection positivity. I don't really need Markovianity as a condition. And then but you need to preserve reflection positivity. Okay, then you start to think, okay, I can preserve reflection positivity and not have so how, starting from a reflection positive process, I can do some perturbation and get another reflection positive process, which maybe it's more interesting. Okay, and then one way to do is to do Gibson perturbation. Okay, so what does it mean? It means that, okay, imagine you have, so now I confound a bit the process with the probability. Let's say that I work in the canonical space of a given process, so the P is just the law of the process and there is nothing else there, okay? And then you can construct a new process. Okay, let us think. P is the law. P is the law of the RP of an RP process. I need a process because I need to work on time, so I just cannot take a random variable. There could be other index, but I don't care. Okay, for the moment I just think to a process. Let's take a finite dimensional, even one-dimensional process, and then you have a reflection positive process with X, the canonical process. Okay, okay, the canonical process. Okay, just okay. Let's think just in this way. Okay, I know that for people who are not used to probability, is a very strange way of thinking, but somehow I got used to it, and it's difficult to go back now. Okay, so omega is a path, so this is a measure on path space. Let's take it like this, and then you want to construct a new measure, which I call Q of t. And so this, imagine a Gaussian, okay? Imagine the Oster-Uhlenbeck process. Then I multiply with this exponential and I normalize because I want to probability measure. And I can take any function, let's say positive, okay? Bounded below would be enough. And okay, this makes sense now, okay? So why I want to do this? Again, because I want to preserve reflection positivity. And when you start to think, it's not easy to preserve reflection positivity. So, and this function, this perturbation preserves reflection positivity. Okay, so you can write, okay, indeed, we can write, so now, okay, the measure Q of t is a reflection positive. So I prove this, and okay, you can call it a lemma if you want. Let's make a lemma. Okay, so this is just to fix the point. So so define a new random variable, and you define it. Take just the positive part of this exponential. Then what you have? Well, then that's very interesting. So what is this? Well, this is certainly G. And okay, what is, okay, let me say, what is theta G? Okay, that's maybe first interesting observation. Okay, remember theta is the time inversion. So theta is G, just to invert the time. Okay, then you think 2 seconds, and this is exactly as doing the integral from minus t to 0. And then, okay, comes maybe not surprised that you can write this as that. And actually, now everything is real, so actually you can write this as that. Okay. Now you want to check reflection positivity. Let's say we introduce this space f of E plus of function which are supported on positive time. Now you want to check reflection positivity. I think you can guess what happens, no? Because you want to check under the measure Q, so I note in this way. Okay. Now I want to check reflection positivity, so I need to go back to my measure P. So let me just note it here. And to go back, I need to multiply with this factor and divide by Z, but of course Z does not play any role here. So this is the formula, and then here, of course, now we can rewrite. So we can rewrite this factor as that, and you see that. Okay, now it's just okay. Now you think 2 seconds, and you have just to put things together. Okay, this is FG, and this is F times G. Okay, and this is positive since P is reflection positive. Okay, so you see that this way of perturbing preserves reflection positivity. And I think actually it's the only way we know to perturb things which preserve reflection positivity. Okay, so let me stop here for now because it's noon. I will continue from there on to discuss this example. I mean, to finish the discussion of this way of perturbing, because this is what will be relevant for us. So far we understood that, okay, we understand a class of reflection positive processes. For us, this will be just Oste-Uhlenbeck, maybe infinite dimensional Oste-Uhlenbeck, but Oste-Uhlenbeck. And then we can do this kind of perturbation, and the Oste-Uhlenbeck, we know it's reflection positive, and we now know that this kind of perturbation preserves reflection positivity. So now we have a larger class. What is the problem of this perturbation? Is that now the process, okay, so let me just cite what is the problem just for this afternoon, but now the problem is that Qt is not translation invariant, okay? Stationary, okay? Invariant under translation. This I need, okay, because in my reconstruction procedure I use this property, okay. So the process has to be stationary and reflection positive. So if you think a moment, when you ask reflection positivity with respect to 0, and you ask stationarity, then actually you can do reflection positivity at any time, not 0. Okay, so there should not be any preferred time, and certainly in this perturbation you single out an interval as a nice. Okay, so that's not translation invariant anymore. Okay, that's not good. So we will have to discuss how from this perturbation you can get something which is translation invariant. So I stop here.